We need to spend some time talking about electronegativity and how this applies to how the molecules are coming together and how this affects this concept of bond polarity. So, remember what electronegativity is. Electronegativity is the ability of an atom within a molecule to attract electrons to itself. So, you've got two atoms sharing electrons, okay, forming a bond. Let's say we're doing a single bond, like shown here for HCl. It's sharing two electrons within this bond, okay? So two electrons being shared, that's why it's satisfying the octet of chlorine and satisfying the duet of hydrogen. Both atoms are more stable because they're sharing the electrons here, but they're not sharing them equally. Chlorine is more electronegative than hydrogen. So chlorine is able to pull the electrons towards itself more than hydrogen. So it's not an equal sharing. It's not like a half and half. They each get half the density here. And so we'd say electrons, but we also talk about electron density, meaning the area of the electrons, the cloud of the electrons. So because chlorine is a more electronegative element, it pulls it to itself more. It's kind of like they're playing tug of war for the electrons, and the chlorine's winning the tug of war. Okay, it's not completely pulling all the electrons away from the hydrogen, but it's still pulling more of the rope towards itself. So for HCl, since chlorine again is more electronegative than hydrogen, the electrons are going to spend more time around the chlorine atom of this molecule. Because of that, though, because there is a permanent dipole, meaning permanent unequal distribution of the electron density, meaning the electrons are hanging around the chlorine more, it produces a polar molecule. That permanent unequal distribution of the electron density, or those electrons hanging around one atom more, is a dipole. Okay, it's an unequal distribution of charge. But because it's happening, it causes the molecule itself to be polar. And so we represent this by writing things like the partial negative and the partial positive above the respective atoms. Partial negative meaning that it has more electron, has more of the electrons more often, or has more electron density, the area of the electrons. This has less electron density. The electrons are hanging around the hydrogen less, so partial positive charge. This does cause the overall molecule to be polar, though. Now, I want to emphasize something. In order for a molecule to be polar, you not only have to have the bond be polar, but the structure of the molecule also has to allow it to be polar. So it's not just the bond being polar that's causing a polar molecule. I'll talk about that in CO2 in a sec. But the different ways we can write this, again, we can see here partial positive, partial negative. Another way we can write it is with this arrow. This is a dipole arrow, and it's showing you which direction the electron density is traveling. This is saying the electrons are hanging out by the chlorine more. And by putting that little line on here, that's telling me it's a dipole arrow. Okay, so it's telling me the chlorine is more electronegative. The electrons are traveling towards the chlorine in this molecule. And then, of course, you can see the space filling model, partial negative, partial positive, the chlorine versus the hydrogen. But notice down here we have CO2. Oxygen is more electronegative than carbon. Why do I know this? Well, because I know my trends. I know fluorine is number one, oxygen is number two, chlorine and nitrogen are tied for third. After that, I follow the trends of the table. But here, if I look at this, this means my electrons are being pulled this way and this way. My two dipoles are pulling either direction. So even though the carbon oxygen bonds themselves are polar, you're going to get polar bonds when you have that just difference in electronegativity. I apologize. Point four is the limit for the difference in electronegativity, and chlorine and oxygen are a polar bond. Most species, unless they're bonded to themselves, will be a polar bond. Not all. Carbon hydrogen is a nonpolar bond. There are a few exceptions. Chlorine nitrogen would be a nonpolar bond. And so we will talk about those exceptions when we need them in class. But most often, if something is not bonded to itself and it's not carbon and hydrogen bonded, it is a polar bond. But here, because the dipoles are pulling in opposite directions, they're canceling each other out, and the overall molecule is nonpolar. So, see what I mean by like to be a polar molecule, you have to have not only polar bonds, but the structure of your molecule has to allow the molecule to be polar. It has to pull the electron density in one way and not be canceled out by a different portion of the molecule. So, how do we tell if it's polar or not? Here's the scale I was talking about. If the difference in electronegativity between the bottom atom is zero, the bond is pure covalent, meaning that it's completely equally sharing electrons. This happens when something bonds to itself. They have the same electronegativity. This happens if you happen to have two elements that have the same electronegativity. You'd have to have the numbers to know they're exactly the same. If the difference in electronegativity between the bottom atoms is between zero point 0.1 and zero point 0.4, the bond is considered nonpolar covalent. A perfect example of this is a hydrogen-carbon bond. Hydrogen is 2.1, carbon is 2.5. Carbon-hydrogen bond is a nonpolar covalent bond because the difference is zero point 0.4. If the difference in electronegativity between the bottom atoms is zero point 0.5 to 1.9, the bond is considered polar covalent. That's what's happening with HCl. The hydrogen is 2.1, the chlorine is 3.0. The difference is zero point 0.9, so the bond here is a polar covalent bond. If the difference between the bonded atoms is larger than 2, the bond is considered to be ionic. So you have to know the scales, you have to know their electronegativities to be able to actually say if it's truly ionic or not. And that's why we talked about this before, but bonding characters can continuous spectrum. So there's things that we treat as ionic, but actually may fall right here, depending on their electronegativity. Okay? So you don't always have the numbers. It comes from practice. It comes from just kind of knowledge behind them. Some of the numbers you don't need to memorize the numbers. That's not what I mean. If given the numbers, you should be able to tell me very distinctly where it's falling. So you need to know these scales. You need to know the scale here. But if not given it, I will have enough information given in class for you to be able to tell me what the bond is. So looking at a few different examples here. Chlorine to chlorine, the electronegativity of each atom is 3, so the difference is 0. It's a pure covalent compound. If I have a HCl compound, the electronegativity of chlorine is 3, hydrogen is 2.1, so the difference is zero point 0.9, and it's considered polar covalent. And NaCl, we know the chloride is 3, because we've said that now 2 other times, but the chloride is 3, but sodium has electronegativity of 1, so the difference, I keep forgetting to fix this slide, 1.0 and 2.0. So the difference overall is 2.0, and it is ionic bond. So let's talk through a couple examples. Of the bonds shown below, which is the most polar? What that means is greatest difference in electronegativity. Well, how do I know? I don't have numbers. But notice they're all bonded to carbon. That's how I can tell. So because they're all bonded to carbon, all I really care about is the other species because they're all being compared to the same number. Even if I don't know carbon's number, I can use the judgment I have for the other species to gauge where this is going to be at. I know carbon bonded to carbon is going to be pure covalent. How do I know that? Because it's bonded to itself. So no matter what that number is, it's going to be 0. I then have nitrogen, oxygen, or fluorine. I may not know their numbers, but I know fluorine is first place for electronegativity, oxygen is second place, and nitrogen is third. So what that means is this will have the most polar bond because it will have the greatest difference in electronegativity.